Hello everyone, we are the Monstars and we'll be talking about small angle neutron scattering today.
The technique starts with a neutron source. Two primary neutron sources are used: steady-state reactors, a constant stream of neutrons produced via fission, and spallation sources, a pulse neutron beam with a frequency of 25 or 50 Hz, via collision of high-energy protons with heavier atoms. Next is the neutron guide tube, a concrete-encased rectangular tube containing multi-layered nickel, or the isotope nickel-58, which has a high scattering length to reflect neutrons traveling through. This piece serves a double purpose, guiding neutrons from the source to the sample and sorting gamma rays from high-energy neutrons. Because neutron reflection is highly dependent on the wavelength, higher energy can be reflected too strongly and extinguished. Gamma rays penetrate the guide tube when they crash into the curvature and are eliminated by the walls. Lower energy neutrons are internally refracted by the nickel and travel down the guide tube towards the sample. Finally, there is the detector. The most common type of detector used in SAS is a gas proportional counter, which is a container filled with two gases. The first gas is an inert detector gas, which ionizes when struck with radiation, and the second is a stopping gas, which makes sure the discharge of the detection gas is terminated. The amount of ionization caused by the radiation is proportional to the energy of the incident radiation. In SAS, the gas proportional counter is a square array which contains multiple tubes filled with the detector gas helium-3 and the stopping gas carbon tetrafluoride. When neutrons impact the tube, the helium-3 will be ionized, releasing charged particles. There are cathodes present in the detector to collect the charged particles and analyze the signal. A square array is used to allow scientists to spatially view where each neutron impacts to show where it was scattered by the sample. The probes used in this technique are neutrons. Specifically, the technique uses the elastic scattering of neutrons, which happen to be between 0.1 degree and 10 degrees, hence the name small angle neutron scattering, to determine information about the structure of the material. When the neutrons come in contact with the sample, they're scattered by neutron-nucleus interaction. Because neutrons have no neutral charge, they are not affected by the electronic charges of the protons or electrons and have no coulombic interaction. Neutron interactions generally occur at distances of 10 to the negative 15th meters, so they generally only scatter once in a sample. Even though neutrons may scatter in any direction, some directions will yield higher intensities. These are the scattering angles that satisfy Bragg's condition. Based on this more intense Bragg scattering, one can determine structural information about the material. Sample prep for SAS is simple. For most samples, there is a sample holder, which is a disc with a thickness between 0.1 and 10 millimeters and a diameter between 1 and 2 centimeters. For a liquid or aqueous solution, a mixture of H2O and D2O is used, depending on the desired contrast. For gels, melts, and powders, the sample can be poured directly into the sample holder and is ready to go. For crystals, the sample is suspended in a tube and placed in the path of the neutron beam. The interaction volume for a typical SAS experiment ranges from 0.1 to 10 millimeters, which is large compared to other techniques because neutrons don't interact with the electron clouds that occupy almost all of the space in the atom. Because neutrons only interact with the nucleus, they are highly penetrating and pass through large amounts of the sample, yielding a high interaction volume for most samples. SAS is most popular among scientists working with biocompounds or sensitive samples. That is because unlike techniques involving X-rays or electrons, SAS is a non-destructive technique allowing the specimen to be left unharmed. Also, SAS is able to detect hydrogen atoms in the sample, which is important in determining the overall structure of organic or biocompounds. Despite its advantages, the method does have its limitations. Due to the large interaction volume of the neutrons, a large amount of sample is generally required to perform an experiment. Neutron sources are also expensive to purchase and maintain, making it difficult to access or own. Long exposure times to the neutron beam are required due to the low flux of neutrons compared to X-rays or electrons, so this method is limited when it comes to time-dependent processes or samples.